let's start maybe with an introduction. Could you introduce yourself? What are you doing? Where are you working? What steps in your career you went through?
Okay, so I'm Shane Bennett. I'm a postdoc at the University of Amsterdam in ultra-cold gases. So I've had a more colourful path than most. I worked for a decade in government and industry, designing and building laser systems. And then I kind of was looking for a bit more of a challenge, so I went into ultra-cold atoms and quantum physics. And that's where I've been for the last almost 10 years. Yeah.
And why did you change? Because it's kind of not a very standard shift from industry to science. I guess most of the people go from science to industry, and you went vice versa.
I was looking for a challenge and a bit more meaning. So we can pretty much do anything in terms of what building lasers. I mean, if there's a need for building something, we can build it. It's I was looking for something where it wasn't clear whether or not it's even possible to do it. I wanted that sort of a challenge.
But then, is it like too risky, or you enjoy the risk?
I think that if you're not doing something that can fail, then you're not taking enough risk. I mean, so for me, I like to be doing something where the outcome is uncertain.
Okay, but taking some risk, I think it's good, but did you try to sort of manage it in a sense? What in the quantum community, in quantum world, you can take different paths, and some paths I think safer than others. But I think you went like really hardcore problems, try to solve hardcore problems, which are really challenging.
For me, I want to try and make something that was impossible when I started possible, and I think that we have done that. And so that's the kind of problem I enjoy tackling.
And before I forget, because I think I will forget, there is a beautiful machine behind you. So can you maybe describe this beautiful piece of equipment, or at least what is building right now, what you're building right now?
So this is our most recent the machine that we're building. It's a new kind of clock. It's a new kind of atomic clock. So it's based on super radiance. So we entangle all the atoms together and get them to emit it as one. And this enables us to hopefully make a much better atomic clock.
An atomic clock, it's a quantum device.
Naturally, it's a tick-tock, 2 qubits, one qubit, 2 levels.
And in terms of like, let's say, quantum world, where's the atomic clock sitting, where it's positioned?
So atomic clocks are kind of well, if you think about a quantum computer, you're talking about something with qubits, so something with a tick and a tock. And so, in some sense, quantum computing and quantum information and quantum simulation, they're all built on the same technology as atomic clocks. So atomic clocks are basically the heart of quantum computers or quantum simulators.
In which sense? Because I think I'm losing you a little bit.
For making the best atomic clocks, you're trying to make a system which is beautifully isolated and has a definite 0 and a 1, just like a bit, and where you can create an entanglement or a superposition between these zeros and ones. And in the same is the task for a quantum computer. You're creating qubits and interacting them. So if you can make a beautiful qubit, you can make a beautiful qubit for a clock, or you can make a beautiful qubit for a quantum computer. And that's why the technology which goes into maybe the most exciting platforms, or some of the most exciting platforms for quantum computers, is exactly the same technology as for quantum atomic clocks.
And let's say if you want to adapt from the platform of atomic clock to the quantum computer, what do you need to do? What's missing in atomic clock to become a quantum computer?
You need interactions. So you need to be able to do functions on neighboring qubits, which is not something you want happening in your atomic clock. So there's a little bit more on top of an atomic clock to make it into a computer.
And is this step like really crucial? Is it hard to get in terms of like, is it hard to build this sort of gap, to fill this gap?
I think there's a number of techniques, or one technique in particular, which is now becoming quite standard. So I think the path for what you need to do to build a quantum computer is fairly well defined at this point. There's a path, at least. I don't know if it's the best path or the only path, certainly not the only path, but I think that the path to building a quantum computer at this point is relatively well defined.
What is this path? What are you referencing to?
So for us, for the technology we work with, it's ultra cold atoms. So arrays of ultra cold atoms in tweezers, and then using Rydberg interactions to create entanglement between neighboring qubits.
Okay.
Process can then be applied many times.
And this is the approach if you want to build a quantum computer. But atomic clock is like a tool by itself, right?
Yes, of course.
And if you look at just an atomic clock, is it like a commercial product, or could it be a commercial product, or it's just a thing which lives in the lab?
So certainly there are plenty of atomic clocks. Atomic clocks have been around for 50, 60 years. So there's plenty of rubidium clocks, which are microwave-based clocks. But the kinds of clocks which we're working on are using optical frequencies. So 3-4 orders of magnitude higher frequencies. And this means that you can get much higher precisions with optical clocks. Optical clocks are not commercially available yet. So we're still trying to make these incredible precisions available more widely. But at the moment, it's still just in labs.
And what's the main challenge? What's the main problem to make this commercially?
So I think it's a lot of engineering is involved, which takes a lot of time and a lot of money. And so I think it's a matter of time. We're seeing already the seeds of several different commercial optical clocks coming up. I think the path is, again, relatively clear as to what needs to be done to make it happen, but it's a lot of good engineering that's needed.
So it's really about time. So you don't need, let's say, extra funding of people. It's just you have to focus on this work and bring it to reality, to bring it to market.
Well, time, funding, material, they're all, if you want to make it go faster, you throw more money at something, or you throw more people at something. I think the challenge is, well, going from something which is in a lab to something which is out in prototyped in the real world, and then going to something which is just commercially available. These are all orders of magnitude in terms of the requirements in each step. So you need a lot of time, people, money to bring something out of the lab and put it into make it robust and reliable and run it in the real world.
But what's the number one missing right now? Because you mentioned a few things which are required, but what's the number one which is missing?
So there is a demand from governments for things like global navigation systems and those sorts of things. There is demand from telecom providers, but at the moment it's I think that the market's still very small, so that's what takes time. So because the market's relatively small, it's it goes a little slower to accumulate all of that engineering work that needs to be done.
I see. And you say that there is a demand, but how is actually happening in a sense? You get the request from some telecom companies or telco companies, or you coming to companies and saying, well, we're developing a product, it might be good for your company. So how is it actually happening?
So this is I think the heart of the problem for a lot of high tech. To see the need for a product, or to justify the use of a new kind of product or a new type of technology, really requires a few prototypes out there and use cases to be developed. And I think once you actually have prototypes out there and the costs start to come down, because those first few prototypes are always very expensive, But once they get out there, then you start developing a market, and that brings the cost down even faster. But before you've actually got those first few out there, it's often not clear how you would use a clock with 20 digits of precision. I mean, your average person is probably not going to want to tell their time to that.
Yes, that's for sure. 20 digits sounds too much. But for some companies, it might be relevant.
For some companies, it is relevant, definitely. But then it's a question of, well, right now there are no commercial clocks available. So there's no commercial providers yet. And yeah. So there is some demand, but if there's no clocks, well, then people will figure out how to work with what they can get.
Yeah, but you mentioned, let's say that now the atomic clock can provide this 20 digit, but maybe there is a commercial analog which can provide, let's say, 18 digits. And is it already sufficient? And it's a robust, if it's a robust product, right? So why let's say, why do I need an atomic clock if I already have something which provides me 18 digits in frequency?
So, well, you can't get 18 digits, so it's maybe 12 or 14 digits of which you can get. And so I think that, again, what a lot of people do, they take their not so great clocks and they lock them to GPS. And that's the technology which is used everywhere at the moment. And so we've developed this huge reliance on GPS signals. If the GPS goes down or something bad happens, then all of these systems will maybe not hold up for very long before you start developing a lot of problems. So it's one of the big challenges, I think, is actually robustness, and that's one of the things which we hope to be able to address once you get these better clocks out there at a reasonable price.
Yeah, but right now when you're talking about still a machine which lives in the lab, right? There are no like really commercially available atomic clocks, even prototypes.
Optical atomic clocks. There are not commercial ones. Microwave clocks are everywhere, but the optical ones are still just living in the labs.
And is there a plan how to move them from the lab? And the point of my question is, one thing is to design a unique machine, a unique device, and another thing to even make a prototype, and completely different stories to make a commercially available product for it. So, and is there like a plan to move the atomic clock out from the lab?
Certainly there are programs to try to partner industry with academia to try to transfer some of that technology out of the lab and into industry, and get industry producing units to meet the demand which is not otherwise being met from, well, particularly governments and also telecom providers.
And so, there are lots of companies which are willing to participate in these sort of projects.
Not as many as you might hope. So again, it's a very fragile market in its first stages. So there's not a huge number of people pulling the technology forwards, and so it takes a little while to get this happening.
And what's the main the engine of the pushing forward the idea of atomic clock?
I think at the moment it's government demands that drive it. I mean, in the US, of course, it's defense, because they tend to be the early adopters of a lot of new technologies. Certainly, robustness of our navigation systems is something which is very important. And also synchronization of all our networks is something which we absolutely rely on, even though it's not something you necessarily see every day.
Yeah, but now what I'm a bit afraid, and I'm not talking about just atomic clocks, but all quantum technology, I feel like the part when the device is moving from the labs to the industry or to commercial products is really lacking. It's really like holding back, I think, the whole quantum world. At least it's my perspective, because one thing is to design something in a lab, and I believe that there are lots of outstanding labs which are designing lots of advanced devices, but then if you look at how many devices I ended up in the market, is really like it's several devices in comparison to the number of labs which are working with quantum devices. It's just enormous misbalance. You see.
I think this is actually a challenge for all technology, and it's something which has been identified the same trend that you notice here. And sometimes it's colloquially called the valley of death for technologies. So technologies receive a lot of funding, firstly in the fundamental concepts, demonstrations. Universities can get grants to try to pursue ideas and create demonstrations of concepts and so on and so forth. And you can sometimes get all the way up to even just sort of lab level prototypes, which is where we are with a lot of quantum technologies. But then you find that it often is very hard to get funding to bridge that gap from the first lab prototypes to getting commercial products out there. And the reason is that I think industry doesn't really want to put the money in to do the product development on new and risky and undemonstrated technologies, because there's a tendency for cost to blow out much beyond what you initially predict. And governments say, well, this is kind of, you've already demonstrated the idea, you've already demonstrated the product. So the number of grants that are available to labs. The second thing is, you don't, universities are built around publications. That's their currency which they rely on. So after you've already got the working prototype there, there's not a whole lot of publications that you're going to get in terms of making it a little bit more robust, or which is needed, but you don't get the publications. So the interest from the university sector kind of falls away as well at that point. So a lot of technologies kind of get to this demonstration stage, but then they're not able to jump this valley of funding. And so I think the challenge for governments, and I think the challenge for us as a society, if we want to actually really use the benefits that a lot of these new technologies, this is not just quantum, this is across the board, is to create mechanisms for actually taking those lab level prototypes and getting them to products. And yeah, I think that's the challenge.
And I think it's really unfortunate in the sense, once you develop a product in a lab and you're already kind of there, let's say that you created the first prototype, you're almost there, and now like the funding is gone. It's really like the worst time. Okay, I understand that probably we have lots of devices in various labs, so you cannot provide funding for every possible devices. But maybe it should be like some sort of grants which support specific, very advanced and the most outstanding products, the most outstanding devices in a lab, and then push them forward to the industry. And as you said, I know that universities are really rely on publications. And it will be nice if at this point, scientific community agrees that, okay, let's not expect publication from this stage of the work in the lab, right? You're just trying to make this, trying to make a real industrial product out of your prototype. And I think it's especially important for the field of quantum technologies, because there are not so many good engineers in the field of quantum technologies. There are good optical engineers, electrical engineers, but the people who can push really quantum envelope, they're, at least in my eyes right now, they're only scientists, because only they understand deeply what's going on under the hood of this quantum technology, right? And they can push it, but right now they don't have funding and they have to focus on publications. And for me, it's like such an unfortunate thing.
I think I mean, I agree in some sense, but I would also say that it's good that we also leave opportunities for new businesses and new companies to grow up, because you don't really want your universities to be just trying to build products. They should be pushing the envelope with new ideas. And
that's fair. Yeah.
So I don't think it's necessarily a bad thing, but we do still have to create those paths and those opportunities to hopefully spin off these technologies into companies and into industry so that we as a society do benefit from these developments. And I think there are ideas out there for how you might do this. So I guess I would say the SBIR program in the US, Small Business Innovative Research Program, is one way in which this is done. I think you need to create opportunities for businesses to adopt these technologies out of these labs. And that means providing funding mechanisms to allow small businesses, big businesses can do this. They have the resources to be able to fund this sort of work. But for small and medium businesses, I think it's often really too risky to branch into these new technologies unless you've already got a background in that. And so I think that programs to allow new entrepreneurs or small businesses to build up prototypes and test and demonstrate a minimum viable product in the market is what you need. You need some funding mechanism to bridge these gaps.
And how to decide which products to fund? In a sense, I know that there are lots of labs which are doing absolutely cool things, and there are, I guess, in every advanced lab there are some devices which could be made commercial, but you cannot fund everybody. So you have to say, okay, let's do at least a few commercial products, and there are not like unlimited budget of money, right? So you have to say, this is really necessary, and let's focus on that. So this, I think, it will be really challenging problem.
So I think that the challenge is to link potential providers with potential end users. And so I think that one way of doing this, at least, is to get the people who are needing these products. So you look at the people building up quantum sensor systems. They know what's needed. They know what the subcomponents are, and so you can put out calls for tender and ask for proposals from business, ask for proposals from young companies and young entrepreneurs to fill some of these needs. So I think both governments and, so in the US, the SBIR program, a proportion of each big department, they set aside a proportion of their funds for funding proposals, and they do calls for proposals for businesses to say, I think we can solve that problem, and then this is a way of funding that.
It's interesting opinion, but now I'm thinking how you would advertise a prototype or an idea which you have in a lab, and you want to advertise it to the world, because now you want to get this funding. And you say, okay, I believe that my device is really the best device, and please give me funding. So, and now we're talking about quantum technology, quantum sensor or quantum computer, and you go into industry, and people who don't work with quantum computers or quantum sensors on daily basis. So for them, it seems like it's some peculiar things which doing some quite complicated, it's still very advanced but complicated measurements, calculations, whatever. And now we're trying to convince them, okay, guys, please join our efforts, and we can do it together. So why they should even risk it? So how you would advertise it to potential, let's say, manufacturing side?
That's an interesting question. And I think, I mean, these things, when they grow up in the labs, they don't grow up in a complete isolation. Here in a lab, I mean, we work with manufacturers right across the country. We work with other providers or other companies to develop subsystems. So I think you'll find that there is a level of, at least at some level of subsystems, there is already some level of experience out there in the businesses and in the community. I think the other thing is, how would they know what to fund? I think there is a demand. There are government departments who will say, we need an atomic clock with this level of precision, because that would enable us to run our network, or hold over our telecommunications system for X amount of days and keep it functioning should the GPS go down. So I think it's a case of just giving the people who already have these requirements the mechanisms to enable them to try to pull these technologies through from the lab a little bit more strongly.
Yeah, and I know that you right now participating or maybe even leading the quantum flagship. I've heard about that, but I really don't know what was the story about it. Is it like the main point of this flagship is to create a commercially available atomic clocks?
That's certainly one of the objectives, absolutely. So as part of the flagship, we are producing, together with industry, partners all across Europe, we're producing prototype atomic clocks, optical atomic clocks. And there may not be commercial products just yet, but hopefully in a few years' time, once these prototypes have been demonstrated and verified, then I imagine our industry partners will be happy to provide this another copy of the product which we've already demonstrated, because the risk levels are much lower at that point. So this is what this one of the objectives of this project is to de-risk these technologies and actually work with industry to show that we can actually produce a working system, suitable system for real world customers. And we actually all go all the way through to telecommunications companies who are our test end users for these products as part of the flagship.
Oh, it's quite interesting. So what you're saying that, and right now the first prototype is behind you on this table.
This is actually a next generation atomic clock. So this is a next level. So right now we've got other parts of the other partners in our consortium working on later generation technologies which are a bit older, so optical lattice clocks, and trying to commercialize those. And those are the technologies we're currently working with industry for. This is a technology which might enable vastly better performance, even higher performance, and hopefully in a much simpler device. So this is about the next generation, the one you see behind me.
Yeah, and I used to work, let's say, with neutral atoms, and I know that these machines takes room and let's say a couple of engineers to run during the day. And now we're talking about a commercial product, or at least prototype, which will become a commercial product. So how it will be as an end product? It will be not a room size device, right?
No, it will. In terms of the clock, it's a couple of racks. So a couple of racks. So it is a mobile, portable system which we can take over to end users and install in their network nodes and synchronize their network. So in this case, British Telecom is one of our end users. So
how much maintenance does it need?
Well, I hopefully it should just run. That's what we're trying to do. That's where we're trying to get to.
So, and let's say the scientific envelope, what is the size of it? What we're talking about, like optical table, let's say 2 by 2, 3 by 3. What's the size?
It's not on an optical table. It's in a rack. So the whole thing's in a rack, including the atomic physics package.
So you mean like vacuum system, electronics?
Everything. It's all rack mounted. Everything's in the system. So yeah.
Wow.
That's the challenge. That's why it takes a lot of time, effort, and money to take things off the table and put them into racks and make all the electronics and get it all working and make sure you don't need a person to actually run it. It will run itself.
Yeah, I probably should explain my surprise, because when I was working with machines which was close to the atomic clocks, it was table, let's say 4 by 2, and probably another table like that. And now you're telling me that it will be just only one rack which contains everything?
Well, a couple of racks, but yes, basically. But all the technologies undergo this evolution, and they start off on tables like the one you see behind me. They will start off on a table with the breadboards of optics, and then we debug it and we find out how to improve it and how to make it properly, and then we bring in the engineers and we shrink it and figure out how to make it robustly and make it rugged so that it will just keep running and running 24/7. And that's what you need for an atomic clock, because the last thing you want is your clock to stop working. That's no good.
Yeah, yeah. I think, and I'm really surprised by how advanced it's already. And what type of engineers working on that? It's okay. I know that scientists, they're mostly like doing everything.
No, certainly. So I think all of the quantum technologies are built upon, all of the technologies that we do in the lab, they're built upon mechanical engineering, electrical engineering, optical engineering, software engineering. We use the full disciplines, and one of the things I kind of like about physics, so experimental physics, is that you actually have to be kind of a jack of all these trades just to get a system up and working. You do have to have some of all these disciplines, and when you actually go out and take a product and try to build it up into a real world system, you have the joy of working with people who are specialists and experts in all these different areas. And as a team, you need to have a team covering all these disciplines to actually bring it out of the lab and into the real world.
So as a scientist, you have to know, as a person who develops this product, you have to know everything. But once you move to industry, it will be optical engineers, mechanical engineers, software engineers. So it will be like specific people dedicated to specific parts of this machine.
I think that's the way you start off like all startups, basically doing everything.
Yeah.
And you do the best you can with it. But when you get people who are expert in the area, who that's their life's work, that's their skill, then often they come up with better better solutions to these little problems. But you start off without those level of resources. So when we're in a university lab, we do not have a team of all these different engineering professions. We have to do all of those things to some degree by ourselves.
And now it's a question, because this is fundamentally quantum device, right? And let's say a standard optical engineer, he can do a very good optical system, but he doesn't know much about quantum mechanics. And is it really important to work with this system to know something about quantum mechanics? Because as a scientist, you do know lots of things about quantum mechanics, but mechanical engineers, they don't.
So I think I think this is where the coordination comes in. So the art of building a team is that not everybody knows everything across the whole team. And so certainly you will have some people who are more on the theory side of things and who can design the algorithms for how a quantum computer might work. And at the other end, you'll have the mechanical engineer designing the vacuum system. And there's a lot of art, I think, in figuring out how to bring all these disciplines together to end up with a working product at the end. But certainly not everybody needs to know every single detail of the entire system. I don't know every detail of the systems that we put together.
You do.
Well, we specialize even within the experimental teams. Like you take care of that piece, and I'll take care of this piece. Otherwise, these systems are just too big and too complicated.
And how many people do you need to build such a machine?
So on the machine we have behind us, we have a team of 4 PhD students at the moment, 2 postdocs, and a master's student who are in some way related to this particular device. And I would say that overall we've got maybe 4 people working full-time on it.
Okay, and how long does it take?
This device, we laid the designs down in August last year. So we're going as fast as we can. So now it's December. So
but it was a Corona time, so it's even surprising that you're delivering something.
Well, we're doing our best to work around the Corona problems. But yeah, so I think the nice thing about universities is that you can go fast and test new ideas quickly, and if they don't work, you move on to the next idea. And that's where this was actually based on a theoretical proposal, which we saw in June. So there was a theoretical proposal which came out of the US, which proposed this design, And we looked into this, and we started sketching up the how we might turn this proposal into reality, and we had designs in the workshop in August.
So you're saying it was like at most 2 months?
Yeah, that's the first. Well, we're just trying to get a working system as quickly as we can, and it won't be perfect, I guarantee. But this is then we can iterate. If we can prove the principle, if we can get it to work in the lab, then we'll be able to improve upon it from there.
Yeah, I think if you're aiming for perfections, it will never leave the lab, because in such complicated machines, there are always things which you want to improve and you want to touch. So
that's very, very true. We're always just go with the best design we can without we don't have the time to analyze everything to the nth degree. That's certainly true.
And to build this machine, you have a good expertise, because I know that you built a machine which is similar to this one, right?
We built a bit more of a complicated machine in the past, yes. So this one's a relatively easy one compared to that one.
So first you built, let's say, some expertise on this machine. You tested a lot of things, and then you moved to another version.
Yeah. So I think part of the trick to being able to go fast is to rely on experience. And so I think if you've got some experience in this area, you have a better feel for what will work and what won't. So you may not have to analyze it in quite such depth to get to a working system.
And how long you've been working in this field, in the atomic clocks, let's say, or neutral atoms?
So I've been working in neutral atoms since 2012. So 8 years, 9 years, 9 years. And I've been working in lasers for 20 years. So
you have like a very decent expertise, right?
I have a bit of background, yes.
So my point is, it's even with such bright people, it takes years to build a first prototype. We're talking about not few months, not even for sure not weeks. We're talking about a couple of years to build a first prototype.
Certainly with a more complicated design. So this one's got a big brother, which is still in manufacture at the moment. And the big brother is certainly a lot more complicated. Hopefully much better performance again, but a lot more complicated. And yes, that will take probably a year or two, if not longer. I'm always underestimating how long these things take. But yeah, it will certainly take a couple of years to get that one up and working.
Yeah, because your heart wants to deliver it faster, but there is always delays. And when you hire new people, what skills, what experience are you looking for?
So we're looking for people who have a passion for it, because in the end they have to love. We don't work 40 hours a week. Maybe we're not supposed to say that, but we certainly don't work 40 hours a week. We will often work 80 or 100 hours a week, and that's just what you need to do to bring these things forward in a reasonable time.
You can mention what time is it and what day it is. I want to mention it's 26th of December. It's Saturday, and it's about 8 p.m. Oh, sorry, 6 p.m. 6 p.m.
Yeah. Yes.
And you're in the lab. So this is like, I just want to, because I used to work with you, so I know how hard you're working. So I think it's very important to understand that these things takes time and a lot of efforts. And I don't know how to describe, how to convey this idea that it really takes a lot of time and effort.
You have to have people who have a passion and want to make this happen. They believe in making the impossible possible, and that's what we are trying to do. We're trying to take something which was nothing but an idea on a piece of paper 6 months ago, and in 6 months' time, hopefully, it will be a working system. Yeah. And so I think that's the first thing I would say.
It sounds very romantic, you know.
Well, we're also very lucky. We're very lucky to be able to do this kind of work and to have it funded. Well, we get to come to work every day, and in some sense, it's just playing. So we get to do what we love every day, and You know, the people who are doing jobs which they may not necessarily love. I've done jobs like that in the past. Then you know that's a bit more of a grind. But I think we we're doing a job which is hopefully going to make a difference in the world, and that's what makes it exciting.
And when I perfectly know. So when you walk in the lab and you're doing something with full of your heart, with huge passion, you don't even notice the time, and you're like, oh, it's time to go home. Really? I still want to do a couple of things. It's
Absolutely. Well, we don't do any work. We just play. We just yeah. It's very exciting, and I think this is kind of what you need. You need to have a passion for this kind of work, and it can't be work. It can't be work. It has to be
passion. Yeah.
fun.
Yeah. But okay, I understand that passion, of course, it's huge if you work in a lab. But what type of skills do you need? Because if you even have a passion, you still have to know something, and you have to have some skills.
Certainly. So we look for a full, well, as I said, so we use the full range of disciplines. So I'm looking, when we're hiring somebody or when we're looking for somebody, we're looking for somebody who knows how to do mechanical design. We like somebody who can do electronic design, somebody who can do software, somebody who can do theory, somebody who can do all of these areas at some level. And when I say do it, I mean they will hopefully have done a project, and it may not necessarily be in exactly this sort of stuff. So I've had in the past when I've hired somebody, I actually had somebody bring a robot in that they'd built, and so you know a robot is for me the perfect example of all of these disciplines coming together. It's something which has mechanical engineering. It has the ability to actually build something. It's got electronics. It's got software. It's got optics to do some vision. You have the full range of skills, and I think that's actually what makes physics such a versatile skill set, because you use all of these different disciplines to some degree, and this can be applied to building a clock, or it can be applied to building a quantum computer, or it can be applied to building a rocket to go to Mars. And so I think that's the beauty of physics. It's hopefully that's what also we're training. We're training people who are versatile with a broad set of skills, who can take up a problem and have a solution to this problem.
Yeah, I agree. It's nice that you mentioned this example of a person bringing a robot to the interview, because sometimes you have a challenge to pick up a right person, which is up to the task. And I think if you bring something, so you're really showing that you can do it. And I think it's very good like tip for the interview, because if you bring something visual, people just they go into it. They really like they look in what this robot could do. It is engagement right away.
I think there's also a big difference between people who talk the talk and people who are actually able to bring it through into reality. So you often see people who speak a lot about all these different things, but there's a whole new level when you actually have somebody who's actually demonstrated the ability to pull these skills together.
Yeah, but I think
a whole new level.
How you find these people who are really passionate about, because in the interview everybody looks nice. Everybody looks nice. But you have to find these people. Do you have like specific questions which you ask on the interviews?
Certainly, we have some questions which are kind of obvious, like
okay, give away a few.
What do you enjoy? What do you enjoy?
But of course, everybody would say that I'm enjoying working in the lab with you. It's like...
Yeah, then I want examples. I want examples of some of the things which you've enjoyed doing, and so we're not really trying to. We're trying to find the kind of person who will enjoy the work that we're doing, because the last thing you want is somebody who is faking it, I guess, in the sense that they won't enjoy it. And I've seen that before. When you get somebody who thinks they want to do this, they think they know what it is, but if they've never actually been into a lab, if they've never done some work in a lab, they may not really have a good idea of what it's actually like to work in a lab. They may think that it's a matter of, you know, like in the movies, you're like, it's all done. It's not. Bashing away at the problem for weeks or months, and then only have it not work, and then going back in there and having another go.
Yeah.
Yeah.
Yeah, I think this is like very important personal traits. And sometimes you see that when you're describing some new interesting research ideas, the eyes are like flashing. You're like, oh my God, now you really get it. And yeah, but sometimes it's hard to find the right person for the task. How big is the group in which you're working?
So our group, our subgroup is maybe
Subgroup is focused on specific task.
yeah. So on this particular project, and there might be 1 or 2 machines in that. So we'll have maybe typically 3 to 5 people, more like 3 typical sort of number for an individual team. And within our group rather large, so we've got quite a few different teams. We've got 4 different teams in our group. Yeah.
And now
But individually, I mean, to my mind, the best number of people is about 3 people for a project. Ideally, somebody who's a bit more experienced, and a couple of people at the PhD student level is what you're aiming for in terms of a group size. Maybe 3 PhD students, 2 or 3 PhD students.
Yeah, now I'm thinking when you mentioned how many people working on the project, I'm now thinking about collaborations. Do you have like a strong collaborations with different people? Because when I'm thinking about projects like a quantum computer, for me, it seems like you should have a strong collaboration between lots of labs, research center, because the task is so huge and so complicated that not even one group can do it, not even one research center could do it. I'm not sure that big companies like Google could do it alone. Like, it still need a huge support.
So certainly the bigger the collaboration, the more specialization you can afford to have, which enables things to go faster and better. Within the IQ Clock collaboration,
IQ Clock is your flagship.
Yeah, IQ Clock is our flagship, our clock development collaboration. We've got, I think, 12 partners.
12 partners.
Yeah, so, and maybe on average, maybe 3 or 4 people per partner.
And between, let's say, different groups which are working on the atomic clocks, because there are groups around the world working on the atomic clocks, do you have like a strong collaboration? Do you like exchange ideas or trying to push each other physical envelope, something like that?
Certainly, I think there is a lot of collaboration between the clock community, within the clock community, and that's largely because if you actually want to measure how good your clock is, you need to measure it against some other clock. You need to have some level of collaboration. So I think that the clock community tends to collaborate quite a lot. Our particular clocks are a different generation, so it's a new type of technology. So I'm expecting that if we can get it working, then we'll hopefully test how well it works against some of the other partners around Europe.
Yeah, actually, now when you mentioned, I'm thinking how you can prove that you delivered a good result, because this is the best result you can get, and now you think, oh, this is the best you can get. Who can prove it that you get it so good?
Certainly that's a challenge. So I think the first thing is to characterize it against the best other systems out there, and yeah. And for a clock, if you really wanted to see how good it is, you build 2 of them. You measure them against each other.
Well, that's smart. Yeah. So you have to build another machine like that.
Usually you build 2, yeah.
And you have the plan to build the second one. And you have the plan.
Oh, certainly. So ideally, if we build 2, there'll be 2 identical clocks, so that we know that the noise is just equal on both of them, for the uncertainties.
But do you see, like, do you want to make a second atomic clock with some improvements already? Do you see, like, okay, now you're working on the first generation of, maybe second generation of atomic clock, and now you say, oh, the third generation, I will do some small changes. You already see there is a room for improvement?
Certainly. So I guess what we would aim for is a second of a similar sort of type would be developed within our other partners. So part of our goals within the collaboration is also to spread the technology throughout Europe, so that all our it's not just one place that has this technology, assuming it works. So yes, we of course do have another generation. I mentioned the Big Brother earlier of this machine, which will hopefully achieve much higher levels of performance. It's not just us that are working on this. We've got other partners in Europe. So, for example, in Toruń, in Poland, they're building a different version of the Big Brother of this one, and so it'll be interesting to see one or both of us able to get those machines working. Then hopefully we'll be able to test them against one another and see how they go.
And is it complicated to make it, let's say, to make an improvements every time? Because right now you're working on something, you see, oh, I can improve it, and you want to probably make it smaller and more robust, right?
So the cycle time for developing these machines is quite long. Yeah. It's in the years, generally speaking. This one here was a very fast machine. We're 6 months in, and hopefully it's more of a 1-year project for this one. But some of the other machines, like the Big Brother of this one, is probably a 2 or 3 year project, and that's the sort of typical cycle time at which you can during the development phase. Of course, we're constantly trying to come up with a better idea or better plans, better designs every day, and we're constantly throwing rocks at the design and seeing if we can come up with a better design. But once we actually go to manufacture, then the hardware is more difficult to change. So it might be on a next iteration of the system that we actually get to do major changes.
And so in the end, you expect that it will be a small device without any maintenance. You just deliver it like a good high-tech advanced tool, right?
Eventually, yes, but there's a lot of steps between demonstrating a concept, which is what we're trying to do in the machine behind us, and getting to a commercial product. So there's many years of work. You can make it go faster with more money and more people, but in the end, there's still a lot of years of work to get.
And let's say, what's the main showstopper? So let's say when you create a first prototype, or you create a Big Brother, this small machine, or when you will be creating the third generation, what is the showstopper? What's like the bottleneck?
In terms of how fast the project can go?
Yeah, so let's say you're saying that right now I can deliver the third generation in a year, and I say, oh, can you deliver it like in 8 months? And you say, no, because there is this problem.
So for us, it took us quite some time to find the right people for the project. So certainly that's always a challenge, trying to
train them, yes.
Yeah, find and then train the people. Yeah, so a PhD student takes 4 years to finish, and that's a journey. That's always a journey. And so you can't just turn things on and off instantly. It takes time, and that's something which all of our partners find. It's always a challenge to find people for a project, and find the right people for a project, because there's that's the objective here.
Find the right people. And you usually, if you're talking about PhD students, finding PhD students, you're looking for a very dedicated master student, right?
We're looking for a master student who is wanting to learn these techniques. So not everybody. A lot of people want to do the theory. They're interested in the theory, but it's often not a given that everybody who has done well in their degree courses or in their theory exams will necessarily make a decent experimental physicist. So an experimental physicist is somebody who knows how to go into a workshop and do machining, can walk up and talk the talk with a mechanical engineer. They can design an electronics board and design a photodiode or a photodetector.
But are you not like asking a lot for a master student, in a sense? Like, it could be a guy with a passion who wants to join it, but he just doesn't have these skills, because this is like really advanced skills. You cannot get everything like right after your master's thesis, right?
Absolutely. Nobody comes in with all of these skills, but there has to be a passion to learn these things. And that's what you're, I think, looking for in this. So you want somebody who actually wants to learn all this. They won't learn everything. Nobody learns everything, but at least we need to do work across all these different disciplines, and we can't hire a team large enough to have specialists in all these different fields. So we need to find a way to. This is, I think, what you're looking for when you get an experimental physicist. You're getting somebody who has this big bag of skills, at least at some level.
Yeah.
That's what makes experimental physics interesting as a discipline.
Yeah, I think you're totally right. And I wanted to ask you another question. And this is related to creating a startup, so establishing a startups.
Mm.
Sometimes I see different labs. There are very good ideas, but these ideas never leave the lab, and people like have this feeling that they should do something with this product, but it never leaves the lab. And what I'm thinking, or what I want to ask is, how to create, let's say, a startup or create a business or make this cool device into the industry. And I think for me, the most natural way to do it is to establish a startup. But now I want to ask you, do you think it's very complicated to create a startup on atomic clocks or another quantum technology? What's your opinion about that?
So for me, the challenge with creating startups in these sorts of high-tech fields is that there's a lot of infrastructure. What does it cost to set up a lab like this? To have that, it's a big risk, and you need to find. We generate a bunch of fantastic, amazing experimental physicists each year. They come out of all these different labs, and a lot of them won't end up in their specialized fields, and the number who end up as academics is very small. So I think there's no shortage of people who would love to take these ideas and turn them into products. These ideas they've been working on passionately for the last few years, and so I think that exists. But we need to have a mechanism for how you do this without getting somebody to risk everything to do it. So there needs to be a way to fund these projects. I think there's also it's a challenge to find a sufficiently small minimum viable product, I guess. So you need to get a company which can actually produce something without necessarily recreating all of what we need to actually create a full atomic clock system. That's the challenge. So there's a lot of you need to find a way to create those funding opportunities.
Yeah, and actually, I think I have quite an interesting question for you. If, let's say, you have a huge budget, I don't know, $10 million, $100 million, and I ask you, would you go for the quantum sensor, atomic clock, whatever you prefer, or would you go for the standard, very advanced technology, let's say semiconductor technology? Where would you go?
Where would I invest it?
Yeah.
So I don't think I could. I think the semiconductor industry is very mature, and I think it would be hard to make a dent into that. There are very advanced firms in the area, and I don't think competing with them would necessarily be a particularly bright idea. You've got something amazing in terms of some novel idea. In terms of quantum technology, I think although a lot of the ideas are quite advanced in terms of what we've demonstrated and integrated systems demonstrations in labs and that sort of thing, but what's missing is the base, the technology base. So often I think that the first challenge is to get the supply chain up and working for quantum technologies, and I think that's something which is still in its infancy at the moment. So I think there are a lot of opportunities there, and I think that you can be somewhat technology agnostic or application agnostic in the sense that if I go and develop laser systems, compact, simple laser systems, cheap laser systems. They'll run neutral atom-based quantum computers. They'll run ion-based quantum computers, simulators, clocks, sensors, quantum cryptography systems.
So you mean that this laser will be suitable for lots of different platforms?
I think the technology there. So I think there's a lot of, yes. That's my short answer. I think there is a lot of opportunities there for making a much more robust, stable supply chain, which will assist in the integration of all of these higher level applications across the board.
And
I think that's where I'd start.
And how to create this basement for the... So you mean that you have to create a basement for the startups to grow?
Yeah. So I think that it's impossible to come in with nothing. If there's not much industry, you have to build the laser systems, you have to build the electronics, you have to build the software, you have to build the vacuum system, you have to build everything. And it's just too big for a startup who's just starting out to be able to do all of that. They don't have the money to do that. They don't have the people or the thing. So if we can get small startups who are doing subsystems, then we can grow on top of that. We can build up the pyramid all the way up to the apex applications, the quantum computers, the atomic clocks, the quantum simulators, which rely on all of these sub technologies. But I think the first step is to really build up from the ground up, and it's not like what we do in the labs where we have a go at everything. We build all our lasers, we build all our electronics from scratch, and that's nice, but you know, it's an enormous task.
But let's say, is it possible to ask for the next grant proposal to create a new type of laser which will be suitable across different platforms, or such a grant would never be funded?
Yeah, I don't think that would be funded. I don't think a grant is well, not a scientific grant, because you're usually looking for scientific impact, which is papers and publications, which is not that sort of grant. So again, I think something like the SBIR type system, where you can basically say, I have this idea for a cheaper, more robust, simpler laser system, which will be useful across all these things. And all I want is to demonstrate that this prototype does what I think it does. Then I think there is an application for, or there's a place for this in terms of SBIR type grants. So I know Holland has an SBIR program. I'm not sure how whether or not it's got calls in the quantum sphere, but I think that's where we need to step. And then once these levels of it, then our job in the labs also gets so much easier, because we can actually go out and buy these subsystems. We don't have to build them anymore, which would be...
But I'm afraid, what I'm afraid of, that it might be a bit more tricky, in a sense that to build this system, you have to really work on a daily basis with these machines, and then you understand what you really need. Because I think people who work with industry, they can build a laser, but they don't know specifically your requirements. So what I'm afraid of, that first you have to start, it's kind of a reverse project. First you have to start understand your requirement, and then I'm afraid that you have to do the first prototype as always, and then this laser exists, and then the industry can pick up, because people who design lasers, they don't know your needs, but the quantum field is so specific that you have to have a very specific products, and the market right now is very limited, so it's hard for industry to jump into it, because only you know what you need.
Yeah. So I think you're right. There's not enough demand to make the existing industry switch to that, or it's not profitable to try to get into these new product areas immediately, because they've got a working system. I do think that we do have a lot of people who come out of the universities who have got a pretty good idea of what's needed, because they've done PhDs, they've done postdocs in these areas. And so I think they are reasonably well placed to be able to start filling these niches. And I think there's a lot of niches to be filled here. So I think there's a lot of opportunities to create companies and to create industries in this field. But it's not always clear how to make that happen. I think it all boils down to the funding instruments that we have, which are maybe not quite there yet.
And what another point which I feel is stalling the progress is it might be that it's hard to understand for standard engineers what the quantum field is, and they're a bit afraid to step into this field because if you don't understand something, you don't want to deal with it, right? It's too complicated, and if you don't understand it, you don't step in.
I agree. So I think that's an issue for existing companies, big companies, and that's where we've got programs like the Flagship, which are about linking existing companies to academic partners who have the experience in terms of they know what's needed for the application, and then they can partner with industry. So I think we do have some mechanisms for that.
And do you know how many flagships exist right now?
I think it's around about 20.
And all of them about quantum technology.
Yeah, quantum technologies, about bringing quantum technologies into things. So there's a lot of industry.
20.
Something on that order.
I mean, okay, 10 or 20, but okay, it doesn't matter if it's like 18 or 21, but it means that if everything goes right, in a couple of years, we can expect 20 new quantum devices.
Hopefully, yes.
Wow. I mean,
some of those flagships are more at the early end, but I think that's the aim. That's certainly the aim.
Yeah, you know, like I think some people might be surprised that it's, oh wow, it's just 20. For me, it's just wow, it is 20. Or even if it's like 11, it's already amazing, because I think some people have quite a huge expectation about the progress and how fast the quantum computing, quantum technology is coming to the real world. But I think I worked for a while, at least in my eyes, the quantum, if you deliver 10 new products, it's already amazing. Don't you think so?
Well, honestly, I think one new product might make a revolutionary impact. So I think one quantum computer, one quantum simulator platform that is robust and large scale and scalable. Personally, I'm a neutral atom person, so I naturally see the evolution of the neutral atom, quantum computing, and I say, well, look, I'm looking ahead, and I'm seeing that growing at an order of magnitude a year, and you know, it's going to happen. It's going to happen in the next few years.
And another point which is a bit puzzling me is how to measure the progress of quantum computing, right? Because in the standard semiconductor technology, we have like Moore's law, that it's double every period of time. But how you measure the performance of quantum technology, let's say, atomic clocks, right? Like, is it like right now it's better than the year before?
Certainly. I think
how you measure it? It's not really measured.
In terms of atomic clocks, we can look at the uncertainty on an atomic clock and how that's evolved, and so this is actually growing much faster than Moore's law.
Really?
So, yeah. So it's doubled in performance almost every year for the last 30 years. So it's going even faster than Moore's law. In terms of quantum computing, depends on how you look at it. But even adding 1 qubit to the system will double the phase space of the system. So if we are doubling the number of qubits, then it's growing extremely rapidly. And right now we're doing a lot more than that. So I think I read a paper just yesterday about a 256 qubit device based on neutral atom.
256 qubit device.
56 qubit device, yes. So it's and this was from a system which 2 years ago was at 50 qubits. So so it's growing rapidly.
You know, like I think for lots of people it might be difficult to comprehend what we're saying. First of all, the numbers, they're not like, you know, millions, thousands, they still like, okay, dozens, they still dozens.
So there was a lot of interest over where quantum supremacy might be. So where is the boundary between what is the best classical computers can do and what quantum computers will beat them? And there's a bit of a debate over to how you should actually measure this, but a number of different groups did some example problems, and they were concluding at around about 50 qubits. They were surpassing the best classical computers with a quantum computer.
It was theoretical prediction.
Oh, this was, I think, it was from Google, I think. So okay. It was, they had their 50 qubit system, and now we're 1 qubit more, double the 2 qubits. We're at 200 qubits more than those 50 qubits now. So I think that the rate at which it's growing is hard to really comprehend in some ways.
Yeah, I think it's amazing. I'm absolutely amazed to hear the number 256. First of all, I mean, for some people it might come as a surprise. They're like, oh wow, it's not like 5 zillions. It's just like 256. It's just, is it a quantum computer? Yeah, like real quantum computer. I remember times when it was like, 2 qubits. Okay, first of all, qubits is just. Can you say what's qubit? Because we just it's such a jargon, so I'm not sure that lots of people.
So a bit is something which is a 0 or a 1, and that's what we play with in classical computing. A qubit is something which can not just be 0 or 1, but it can also be some sort of superposition of the two. And so when we're talking about qubit systems, we're talking about multiple qubits, which can also be all entangled together.
And when we're talking about,
that's why it grows so rapidly in terms of its.
Yeah, but and when we're talking about, let's say, standard computer in terms of bits, I don't know how many bits right now the standard computer has. Let's think your recent MacBook has like, I don't know, millions, zillions. I don't know what's the number for bits. But if you're talking about quantum computer, it's like, okay, a few hundreds of qubits. So it's like the number's not even compatible, but the calculations which you can do, the stuff which you can do is really like the next level. That just with 256 qubits, it's just completely different level of measuring. And I think it might be hard for some people to comprehend that now it's like a different game which we're playing. So you cannot really look at the numbers with your old perspective.
Yeah, so I think that's actually one thing which is very important to remember. The kinds of problems that you'll tackle with quantum computers are not the same as what you tackle with classical computers. And so I don't think a quantum computer will ever be useful in your phone, in your laptop, at least not anytime soon. Maybe you'll use a cloud device to speed up certain calculations, but I don't think you're going to put a quantum computer into these portable devices. They're useful to tackling very specialized problems. So where problems like how do you calculate how a molecule folds, or how do you design a new drug or the medicine, or how do you crack a crypto problem.
Already hacking something.
These are the or how do you protect your information? So these are the sorts of problems which quantum computers and quantum cryptography and quantum simulation are targeting. And they're not the kinds of they're not necessarily consumer type problems.
Yeah, I think like it what I'm afraid is there is quite a misunderstanding, let me call it this way, let's say public perspective, what the quantum computer will do. And there is, I already heard a couple of times when people ask me questions like, when the quantum computer will be sold on the Amazon? And you're like, I mean, like 100 years? I don't know, 200 years?
Well, I think Amazon's selling you access to their quantum computers.
Yeah, but
you can run an algorithm on a quantum computer at Amazon, but I don't think you're ever going to want to buy a quantum computer unless you're a big company doing these sorts of big problems.
Yeah.
So maybe AI is maybe the area where we will actually sort of use a quantum computer or a quantum algorithm, but it's probably going to be under the hood. So the actual consumer will maybe not even realize that they're actually using these things. But that's all for the future.
Yeah, no, I think the point is to realize I'm not sure what's the best platform right now for quantum computers, but I guess it still takes room and a couple of engineers just to see that it's really aligned, calibrated and prepared for working time. So, and this might be, I guess, boggling some people that it's really like a room. It's like old 60s for computers, or I don't know, 50s. I don't remember what the time was. It's really like rooms with a bunch of engineers running around.
Yes, yes. At the moment, yes, very much so. Yes.
Yeah, so I think it might be shocking news for some people, because and I think the public just perspectives, there is nobody explained what the quantum computer is, but people start talking what the quantum computer will do and how fast it's coming. But I don't think there is a ground of knowledge where you can build upon these jargon words. Like, oh, right now we have 256 qubit. How big is this? Oh, it's enormous computational power, but it's just 256 of what? Like, you have to understand what's the qubit, what's the quantum gate.
Yeah.
So, yeah.
So at the moment, I think that the real test for quantum computing or quantum simulators will be what difference does it make in the real world? What difference does it actually make to people's lives? And I think that's still a little ways off. But I'm hopeful that there'll be a quantum coprocessor which you'll be able to use to solve these very hard problems in science, and that will in turn translate into real world benefits for people. So I'm looking forward to a whole bunch of new medicines which can cure our ills and
Especially in terms of corona.
Maybe, yes. Maybe we'll be able to design these things much faster, hopefully in the future.
And I think you bring up another important point, that quantum computer is really suitable for very specific mathematical, physical, chemical tasks. It's not like it's suitable for everything. There are very specific, at least for now, there are very specific tasks which you can address with the quantum computing, quantum technology, sensors, whatever, but it's very specific task. It's not like everything.
No, it's not everything.
Yeah. I think it's a very positive moment, and I guess it will be a nice moment to stop our discussion. I really enjoy talking to you. Every time I'm talking